Space radiation is fundamentally different from the kinds of radiation we experience here on Earth. Here is every type of radiation in space, explained in full. Let's break this down. Galactic cosmic rays. Galactic cosmic rays were the most ancient, the most energetic, and the most difficult to shield against of any radiation source in the space environment. High-energy protons and heavy ions that originated outside the solar system, accelerated to velocities approaching the speed of light by the shock waves of stellar explosions and other extreme astrophysical events across the Milky Way, and arriving at Earth's orbit after journeys that had in some cases lasted millions of years. Space radiation is comprised of atoms in which electrons have been stripped away as the atom accelerated in interstellar space to speeds approaching the speed of light. Eventually, only the nucleus of the atom remains, a bare charged nucleus moving through space with an energy whose specific value was determined by the particular combination of astrophysical processes that had accelerated it. Primary galactic cosmic rays comprise protons and high-energy, heavy-ion charged particles, designated HZE particles, high-energy, high-atomic number nuclei, with energy spectra forming a broad peak around 1 GeV per nucleon, the gigaelectron-volt per nucleon being the energy scale at which the particles were most numerous and most biologically significant. The particles consisted of all known stable element nuclei and electrons, but were dominated by protons and electrons, followed by helium, and then all of the heavy ion nuclei, such as carbon and iron. The iron nuclei being the most biologically damaging per particle due to the combination of high charge and high mass that made their ionizing track through biological tissue particularly destructive. The specific biological hazard of galactic cosmic rays was the hazard of ionizing radiation whose penetrating power was high enough to pass through any practical thickness of spacecraft shielding while still carrying enough energy to cause biological damage as it passed through. The characteristic that distinguished GCRs from lower energy radiation sources and made them the dominant long-term radiation concern for any crewed mission beyond the Earth's magnetic field. An astronaut on the International Space Station received a radiation dose from galactic cosmic rays of approximately 80 millisieverts per year from this source alone, compared to the 2.4 millisieverts that the average person received from all natural sources in a year at Earth's surface. And an astronaut on a 6-month journey to Mars would accumulate a total dose that approached or exceeded the career radiation limit that NASA set for its astronauts, with galactic cosmic rays contributing the majority of that accumulated exposure. Solar particle events. Solar particle events were the most dramatically variable and the most acutely dangerous radiation source in the near-Earth space environment. Sudden releases of energetic particles from the sun during solar flares and coronal mass ejections, whose intensity could rise from background levels to life-threatening doses within hours, and whose specific unpredictability made them the most operationally challenging radiation hazard that space mission planners had to account for. These solar flares can have serious consequences to astronauts and their equipment, even at locations far from the sun. The statement from NASA communicating that the distance from the sun did not provide the protection that intuition suggested, because the energetic particles released during the most powerful solar particle events were accelerated to sufficiently high velocities that they reached the orbit of Mars and beyond in time frames of minutes to hours. The particles released during a solar particle event were primarily protons, with the proton flux during a major event capable of rising by several orders of magnitude above the background level in the time between the detection of the initiating solar flare and the arrival of the particle shower at the spacecraft's location. The 1972 solar particle event, which occurred between the Apollo 16 and Apollo 17 lunar missions, was estimated to have delivered a dose that would have been lethal to any astronaut on the lunar surface without adequate shelter, the event occurring in the gap between two crewed lunar missions rather than during one being the specific circumstance that prevented it from becoming the worst space radiation accident in history. An astronaut in space during the 1972 event with no shielding would have received a dose equivalent to many times the lethal threshold. The near miss communicating that the specific timing of crewed missions relative to the solar cycle and the specific prediction of solar particle events was not simply a scientific concern, but a direct life safety operational requirement. Hit the like and subscribe button to see more videos like this. Leave a comment on what radiation type surprised you most. Let's get back into the video. Van Allen belt radiation. The Van Allen radiation belts were the zones of trapped energetic particles that surrounded the Earth in two distinct donut-shaped regions, occupying altitudes from approximately 640 to 58,000 kilometers above the Earth's surface, within which radiation levels varied dramatically with altitude, latitude, and the current state of solar activity. The belts were in the inner region of Earth's magnetic field and trapped energetic electrons and protons, the trapping mechanism being the Earth's magnetic field lines that captured charged particles and forced them to spiral back and forth between the magnetic poles in a continuous bouncing motion, creating a permanent population of energetic particles that had accumulated over time from both the solar wind and cosmic ray interactions with the upper atmosphere. The term Van Allen belts referred specifically to the radiation belts surrounding Earth, but similar radiation belts had been discovered around other planets, Jupiter's radiation belts being the most intense in the solar system, hundreds of times more energetic than Earth's, and a critical design constraint for any spacecraft attempting to study Jupiter up close. The inner Van Allen belt extended from approximately 640 to 9,600 kilometers above Earth's surface and contained primarily high-energy protons, whose energies of tens to hundreds of mega electron volts gave them sufficient penetrating power to damage both biological tissue and electronic components in spacecraft passing through. The outer belt extended from approximately 13,500 to 58,000 kilometers and contained primarily high-energy electrons whose energies were lower than the inner belt's protons, but whose flux was higher and whose specific interaction with spacecraft electronics created the surface charging effects that could damage satellite systems. The South Atlantic anomaly was the specific area where the inner Van Allen belt dipped closest to Earth's surface, above Brazil and the South Atlantic Ocean, where an impressive flux of protons and electrons reaching 100 to 1,000 protons per square centimeter per second at 500 kilometers altitude created the most radiation-intense region of Earth's orbital environment, a region that satellites in low Earth orbit passed through multiple times per day and that the International Space Station crossed regularly, with the specific elevated radiation dose during each pass being monitored by onboard dosimetry systems whose readings informed astronaut activity scheduling. Gamma rays. Gamma rays were the highest energy and shortest wavelength form of electromagnetic radiation in the universe, photons, whose energies extended from tens of thousands to billions of electron volts, and whose sources in space included pulsars, black hole accretion disks, neutron star mergers, supernova remnants, and the most extreme astrophysical events that the universe produced. Gamma rays, X-rays, ultraviolet light, visible light, infrared light, microwaves, and radio waves were all forms of electromagnetic radiation, but gamma rays occupied the extreme high-energy end of this spectrum, their photon energies being high enough to penetrate most materials that blocked lower-energy radiation and to ionize biological tissue directly rather than through the secondary effects that characterize the lower-energy radiation types. The specific sources of gamma rays in space were the sources of the universe's most energetic events. Gamma ray bursts were the most energetic explosions in the observable universe, releasing more energy in a matter of seconds than the sun would emit over its entire 10 billion year lifetime. The long-duration gamma ray bursts, lasting from 2 seconds to several minutes, were associated with the collapse of massive stars at the end of their lives, the initial burst of gamma radiation being the most energetic component of the supernova event, whose lower energy counterparts were visible as supernova across the electromagnetic spectrum. Pulsars, rapidly rotating neutron stars that emitted beams of electromagnetic radiation from their magnetic poles, were among the most powerful gamma ray sources in the Milky Way, with the Crab pulsar generating a gamma ray luminosity that astronomers use as a unit of brightness for other high-energy sources. The Fermi Gamma Ray Space Telescope, launched in 2008, provided the most comprehensive mapping of the gamma ray sky available, revealing a universe whose gamma ray structure was dramatically different from its visible light structure. The gamma ray sky dominated by high-energy sources whose distributions communicated the locations of the most extreme physical processes in operation across the observable universe, X-ray radiation. X-rays in space occupied the portion of the electromagnetic spectrum between the most energetic ultraviolet radiation and the least energetic gamma rays, photons whose energies range from approximately 100 electron volts to 100,000 electron volts, generated by some of the most extreme and most scientifically informative environments in the universe. The primary sources of X-rays in space were sources of extreme heat and extreme gravitational energy, accretion disks around black holes, where infalling material was compressed and heated to millions of degrees before crossing the event horizon, and the energy released as X-rays. Neutron stars, whose surface temperatures of millions of degrees made them among the most luminous X-ray sources per unit surface area in the galaxy, and hot plasma in galaxy clusters, where the gas between galaxies reached temperatures of tens of millions of degrees and radiated primarily in the X-ray band. X-ray astronomy had provided the most direct evidence for the existence of stellar mass black holes. The binary star systems in which a normal star orbited a black hole, with material stripped from the normal star forming an accretion disk around the black hole that radiated X-rays, whose intensity and variability communicated the mass, spin, and accretion rate of the invisible black hole companion. The Chandra X-ray Observatory, launched in 1999, was the most sensitive X-ray telescope ever built, resolving X-ray sources whose angular separation was as small as half an arcsecond, comparable to the resolution of the best ground-based optical telescopes. The X-ray radiation environment in space was also a direct concern for satellite electronics. The energetic X-ray photons produced during solar particle events and from background cosmic sources contributed to the total ionizing dose that spacecraft electronics accumulated over their operational lifetimes, with cumulative X-ray exposure being one of the factors that determined the radiation hardening requirements for satellite components operating in high radiation orbits. Ultraviolet radiation. Ultraviolet radiation was the form of electromagnetic radiation immediately beyond the violet end of the visible spectrum. Photons, whose energies were sufficient to break the chemical bonds in many biological molecules, and whose interaction with DNA was the primary mechanism by which exposure to intense ultraviolet produced the cancer risk associated with excessive solar exposure on Earth. In space, ultraviolet radiation was far more intense than on Earth's surface, for the specific reason that Earth's atmosphere absorbed the most biologically damaging short-wavelength ultraviolet radiation before it reached the surface. In space, UVC, with shorter wavelengths than UVB, was much more prevalent, and its intensity was much higher than on Earth. The ultraviolet environment in space was classified by wavelength into UVA, UVB, and UVC bands, with UVC, the highest energy ultraviolet band, being completely absorbed by Earth's atmosphere before reaching the surface, but present in the space environment in quantities that would damage unprotected biological material in minutes. The ultraviolet environment was also a significant operational factor for spacecraft materials. Polymers, adhesives, coatings, and flexible materials used in spacecraft construction all experience ultraviolet-induced degradation in the space environment at rates that were dramatically higher than any ground-based aging test could simulate, because the vacuum ultraviolet component of the solar spectrum was only present in space. The ultraviolet universe observed by space telescopes, Hubble's ultraviolet observations, the Galaxy Evolution Explorer's survey of ultraviolet bright stars and galaxies, revealed a universe whose ultraviolet structure communicated the locations of the youngest and hottest stars, whose surface temperatures were high enough to radiate primarily in the ultraviolet rather than in the visible wavelengths that characterize cooler stars like the Sun. Infrared and radio wave radiation. Infrared radiation and radio waves represented the lowest energy end of the electromagnetic spectrum relevant to space science. Photons whose energies were insufficient to ionize biological tissue, but whose information content was among the richest available to astronomers observing the universe's structure, formation history, and current physical state. Infrared radiation, immediately below the red end of the visible spectrum, was the primary wavelength regime in which the universe's coldest objects and most distant receding galaxies emitted the majority of their detectable radiation, dust clouds in the interstellar medium that were too cold to emit visible light, but whose temperature of tens of Kelvin made them bright in the far infrared, and galaxies at cosmological distances whose visible light emission had been redshifted into the infrared by the expansion of the universe that had carried them away from us at significant fractions of the speed of light. The James Webb Space Telescope's infrared instrumentation was the most sensitive ever deployed in space. designed specifically to observe in the near infrared and mid-infrared wavelength ranges where the first galaxies and stars to form in the universe were visible at the redshifts produced by their enormous distances. Radio waves represented the longest wavelengths in the electromagnetic spectrum. Photons whose wavelengths range from millimeters to kilometers, and whose sources in space included pulsars, the cosmic microwave, background radiation that was the afterglow of the Big Bang itself, neutral hydrogen gas in galaxies in the interstellar medium, and the jets of energy produced by supermassive black holes at the centers of active galaxies. The cosmic microwave background, the radio frequency radiation filling all of space at a temperature of approximately 2.73. Kelvin was the most information-rich single astronomical object in the universe. Its tiny temperature fluctuations encoding the initial density variations that had eventually grown under gravity into the entire large-scale structure of the observable universe. Every galaxy, cluster, and every cosmic filament ultimately traceable to the specific pattern of fluctuations imprinted in the radiation that had been released 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons, and space became transparent to electromagnetic radiation for the first time.